Now that we have a lot of integration techniques under our belt, we're going to start using definite integrals to find area and length. This is where we start. So we know that if we want to find area under a curve, so say we had this function f of x, that we can use integrals to find area under a curve. Say we wanted to find the area from -4 to 3 that is sitting between this curve and the x-axis. So all of this area here. When we were first finding area under a curve, we used to estimate it with rectangles. We would take a bunch of little skinny rectangles, and the width of these rectangles we would call delta x. And then the height of the rectangles was always just the function itself, so f of x. And we would add all of them up. We'd have, tons of rectangles. And as delta x went to 0, or the number of rectangles went to infinity, this became an integral. And it was at first an estimate of the area under the curve, but as you take the limit as n goes to infinity, it becomes the actual area under the curve. And so this is not new to us. We know that that area under the curve is represented by the integral of f of x dx. And in this case, we wanted to go from -4 to 3. So this is area bounded by f of x and the x-axis between x equals -4 and x equals 3. This is just one of the interpretations of the integral. So here we still have f of x, our regular curve that we were just talking about, but now we have a new curve that's sitting right here. We'll call this g of x. And say that we wanted to find the area between f and g, so we wanted to somehow calculate this area in here. Just like before, we can think about rectangles, and we could take a rectangle between these two curves. And again, this width of the rectangle is delta x. But this time the height of the rectangle is our top curve, which is f of x. And we can't take all of f of x, that would be too much, so we take f of x, but then subtract off this little portion here, which is actually equal to g of x. So the length of this rectangle right here is f of x minus g of x. And we have to think, does that work even if, sometimes g of x actually dips negative? Would that still work? Would the rectangle still be called f of x minus g of x? So let's think about this for a minute. Here we would have delta x, and then we still want to count the whole length of this rectangle, so this length would be f of x. And this is actually a negative number here. So we're going to, if we were to take f of x minus g of x still as our length of the whole rectangle, that would be accurate because you have f of x minus a negative number, which is g of x. And so those two negatives cancel out and create the length that we want here. So we would have f of x minus some negative number. So f of x minus g of x does give us the length of this because those two negatives will turn into a positive. Okay, so even if one of the curves dips below the x-axis, it works. So we become very interested, like if we were asked to calculate the area bounded by these two curves, we do become interested in these endpoints, and we would have to find the starting and stopping point for where we want to count our integral. But still here we would have some a starting point, a stopping point. We'd have the top curve minus the bottom curve and all of that. The integral of this expression, dx, will equal the area bounded by the two curves. And just knowing that we're going to have to calculate that starting point a, x equals a, and a stopping point, x equals b. So this would be a typical problem. Find the area of the region bounded above by y equals x, e to the x, and bounded below by y equals x, and bounded on the sides by x equals 0 and x equals 1. I'm going to go ahead and graph these functions to see kind of what the region looks like. So here we have the two functions that they've given us. This is y equals e to the x, and then we have y equals x here. And they've told us that they want us to only go from x equals 0 to x equals 1. So we're interested in just this area right in here. And that will be represented by the integral, the integral from 0 to 1. The top curve is e to the x minus the bottom curve, which is just x. And this is relatively easy to find out. E to the x minus x squared over 2, evaluated from 0 to 1, is e minus 1/2 minus e to the 0. So e to the 0, or 1, minus 0. This is e minus 3/2. And we can leave it like this, or we could get a decimal approximation for this. This is relatively simple, looking for area between two curves. So our next example, find the area of the region bounded by the curves y equals x over square root of x squared plus 1 and y equals x to the 4th minus x. These are two slightly more complicated functions than the one before, but this is a good one to try on your own. So pause the video and see if you can calculate this area. Feel free to use Desmos. Feel free to ask Desmos to integrate anything that you want it to integrate. So we're at the point where we're going to ask Desmos to do a lot of the integrations for us. We're going to set things up, and then it can do a lot of the calculations. So I'm going to put my first function in, the green one, and then I'll put the y equals x to the 4th minus x. And so I'm starting to get a picture of what these two functions, you know, you might ask, well, which area are we looking at? And it will be the finite region that these two graphs encompass. There's regions over here, there's regions up here, over here, but we're going to look at this region right in here that is a finite region. So this is the area bounded by the curves. And I'll ask Desmos for these starting and stopping points. So we'll just click on the point of intersection and this other point of intersection. So we can see that we're interested from 0 to about x equals 1.18. So we'll ask Desmos to give us that integral. From 0 to 1.18078 of the top function minus the bottom function. And I don't want to have to type these functions in again, so I'm just going to quickly change their names to f of x and g of x. And then we can just ask Desmos to give us f of x minus g of x. With respect to x. And it will give us the area of those two functions. So in this example, Desmos was able to do most of the work for us. We just asked it to find the integral from the left-hand point to the right-hand point of the top curve minus the bottom curve, and it was able to give us this solution. So this is our third example. Find the area of the region bounded by the curves y equals sine x, y equals cosine x, x equals 0, and x equals pi halves. And this is going to give us a sort of a cautionary tale to not jump too far ahead without really understanding the situation. I'll give you sort of the erroneous solution. If I just said, okay, I'm going from 0 to pi halves, and I know that at 0, cosine is above sine of x, so I'm just going to say, we're going to say cosine x minus sine x dx. If you actually calculate this, you can do it by hand, or you can ask Desmos or another tool to do it for you. The solution is 0. But that's not correct. So what's happening here? So this is now a picture of what's happening. We have, this is our our y-axis and our x-axis here. And we know that we're bound by x equals 0 and x equals pi halves is right here. We do start off with this curve y equals cosine of x right here. And then we have the curve y equals sine of x, and definitely cosine x does start out as the top curve, so it would be right to take top curve minus bottom curve, but only until here when all of a sudden sine x becomes the top curve and cosine x becomes the bottom curve. So when we were doing this, calculation for the whole interval 0 to pi halves, we were essentially counting up some area and then taking the negative of that area, because then we were taking cosine x minus sine x, which would flip it, and we were zeroing everything out. But we are interested in the actual region bounded by these two curves, so it will be a positive number for both of these areas, and so we just need to split it up. So whereas this was the wrong solution, the correct solution would look something like this. We're going to count up from 0 to some point where they intersect, cosine x minus sine x dx. And to that we'll add, well, we should figure out what point this is. This is the point. It's halfway between 0 and pi halves. It's pi fourths. So 0 to pi fourths, we're counting up the area cosine x minus sine x. And then from pi fourths to pi halves, we need to count up the area sine x minus cosine x dx. This integral will be counting this area, and this integral will be counting this area. And this is sometimes necessary. It's not that uncommon that two curves that you're interested in finding regions between will intersect, and all of a sudden the one that was on top becomes the one that was on the bottom, and you have to figure out how to divide up that integral. And this first integral becomes, if you calculate it, square root of 2 minus 1. This integral becomes square root of 2 minus 1. And so we have 2 square root of 2 minus 2 for our final solution. This is counting the area of all of this pink region in here. So this next example is going to introduce something new where we will need a new technique. Find the area bounded by y equals x minus 1 and y squared equals 2x plus 6. So after we get kind of situated with this problem, we'll see that we'll benefit from a different approach. So we'll need a new technique here. And let's get a picture of what's going on. So this red curve is the curve y squared equals 2x plus 6, and the blue line is y equals x minus 1. And you probably, in the area that we're interested in calculating or finding out what it is this area here, the region bounded by those two curves. And already you probably are figuring out what makes this problem a little bit different than the previous ones. This curve here is not a function, and if we were to try to take rectangles and add them up like we were in the previous examples, it would be a slight problem because at x equals negative 2, for example, this red curve here is not a function, so y squared equals 2x plus 6 is not a function. And if we tried to, sum up some rectangles, a bunch of rectangles here, the problem that we immediately run into is the width of this rectangle is fine, but the length of this rectangle is the top of your curve and the bottom of your curve are the same function. And so that seems to be a problem. We could kind of do a workaround where we said, okay, from this point to the right, we can definitely do these vertical rectangles and sum up that way, and we can figure out a way to do this area kind of a more creative way. But instead of doing that, what we're going to do is to solve this problem, we're going to, instead of using vertical rectangles, we're going to use horizontal rectangles. So we're going to take a rectangle that looks like this to estimate the area, and then as we take the number of rectangles to infinity, it will be the exact area. But now instead of, so this width of the rectangle right here, this is a small change in y. So this is now dy or delta y. And then the length of this rectangle would be whatever this right function is minus the left function, the value of the x value on the left function. So the x value on the right function minus the x value on the left function will give us the length right here. So for example, this is kind of close to 1. This is pretty much right on negative 3. So if we take the right function, 1 minus negative 3, that'll give us 4. And that is the length of a potential tiny rectangle right here. We do that all throughout this region, just taking rectangles. And so what we end up with is we're going to calculate this area by taking the integral from a lower y value to an upper y value. So some y equals a to a y equals b that we'll find. And we're going to take the x value on the right function minus the x value on the left function times dy, because now we're the width of these little rectangles are a delta y, and the length are the difference of the x values. So this is a horizontal rectangle. Instead of adding up a bunch of vertical rectangles, we're going to add up a bunch of horizontal rectangles. And this this length right here is just x to the right minus the x value on the left. The process is really the same. We just have to make sure that all of the pieces are representing the right values, whether it's x or y. So here we've got to figure out, do we want -1 or -2 for our starting point? And we want that lower y value, so -2. And then right here, we want the upper y value, so we want to do 4. So this is the only slightly tricky part, is keeping your x's and y's straight. We want the lower and the upper y values here. Now we want the x value on the right. So what would be wrong with saying x minus 1 minus, something like a square root of 2x plus 6. So this is not correct. And why isn't it correct? It's because you're essentially taking difference of y values here, but we really need difference of x values. So that's not going to work. We need difference of x values. So we have to think about these guys. This says that x equals y plus 1. And this one here, this relationship, says that x equals, let's see, y squared minus 6 divided by 2 is what x equals. So these are the, let's see, this is the left x value and the right x value that we want to use. This will be xl, and this here will be xr. And so that is the trickiest thing in a problem like this, is just making sure that you're summing up the rectangles using the right variables. How do we know if we want to use vertical or horizontal rectangles? I mean, typically you're going to use vertical ones because the functions that we're given, the expressions that we're given usually are functions. But really the best way to know is to draw out the situation, and you can kind of tell immediately, oh, vertical rectangles are not going to work here, so let's try horizontals. And they definitely work a lot better. Okay, so let's finish this one out. We know that we want the x value on the right, which is this, the x value of this expression, minus the x value on the left, which is representing this relationship. And so we want y plus 1 minus y squared minus 6 over 2, and all of that is going to be times dy. And this is the integral that we want to evaluate. We can clean it up, and we could evaluate it by hand pretty easily. -2 times 4, there's a -1/2 y squared, there's a plus y, looks like there's a plus 1, plus 3, so a plus 4 dy. This is a relatively simple integral to evaluate by hand. You could also ask Desmos or some other aid to help you, and the answer should come out as 18. This is the area of the region bounded by those two curves. So this region here. So sometimes better to use horizontal rectangles. And if we do, then this is the relationship that we want to be counting. So what we've seen is sometimes we're going to add up a bunch of vertical rectangles, an infinite number actually, to get what we need, and sometimes we add up a bunch of horizontal rectangles. Both of these are when we were looking for calculating an area between curves. So we know how to do that. We know how to do that. The next thing we need to do is talk about something that's related but different, which is finding arc length. So this is finding the length of a curve from one point to the next. So for example, we might have a curve that looks like this. And say that we wanted to find the length of this curve at some particular starting point to some particular ending point. How would we measure how long this curve is? Like say we wanted to be able to measure the length of this segment of the curve right here. So one way to do this is we're going to take a bunch of really just line segments along the curve. So we're going to kind of pretend that we're just going to add up a bunch of straight lines. Like we're going to take points on the curve, just create a straight line between them, and add up these straight lines. Whoops, that's not very good. So more like that, and that straight line, that straight line, that straight line, that straight line. So when we're adding, we have to know, what is the length of at least this segment of the line. And we can think of this as the hypotenuse of a triangle. And the triangle might look like this, where you have a small delta x here and a delta y here. Then what would the length of this hypotenuse be? Well, the hypotenuse would be, just by Pythagorean theorem, the hypotenuse will be, let's see, delta x squared plus delta y squared will be the hypotenuse squared. So the hypotenuse will be this length here. And we want to add up a bunch of these little hypotenuses, one right here, one right here, one right here, just for different delta x's and delta y's. So I'm going to do a little bit of algebraic manipulation with that hypotenuse length. So we already decided we need to add up a bunch of these all along the curve, and that will give us the total length, or an approximation of the total length. So I do want to kind of like sum all these up and an infinite number of them, and that would give me, all along the way, eventually the length of this curve. But I'm going to clean it up in a way that it will be easier to integrate. And the first thing I'm going to do is I'm going to pull out a delta x squared. As it comes out of the radical, it'll turn into just delta x. And of course I can't just take it out of one piece, so let's do it like this. Delta x squared 1 plus delta y squared divided by delta x squared. So this is totally legal to do. I've just factored out a delta x squared, and as it comes out of the radical, it'll be just a delta x. And then inside I have a 1 plus delta y squared over delta x squared. This is like a delta x. 1 plus, this is really just another way of saying dy over dx squared. So this is a little change in y over a little change in x. Both of them are squared. And this is just the first derivative squared. So this equals delta x times 1 plus whatever our function is that we're trying to find the arc length of squared. Okay, and then this will act as our dx. And then now it does look like something that we probably could integrate. So the area, the arc length of any curve will equal the integral from your starting point to your stopping point of the square root of 1 plus the derivative squared, and then dx, and that dx is just coming from this delta x here. So this is a formula for arc length that we can use. If we ever want to measure, and we will, the length of a portion of a curve, this is what we can use, and this is why we can use it. Okay, here's our last example for this section. A moving particle is traveling along the curve y equals f of x equals 0.1x squared plus 1. So there's this curve at a rate of 7 centimeters per second. And the x and y coordinates are measured in centimeters. So just a note, this function is not a position function. It is the actual path that the particle is traveling. So curve is not a position function, but it's a path traveled. It is a path that the particle is on, traveled by the particle. So let's see if we can get a picture of what's going on here. So this is the curve y equals 0.1x squared plus 1. And so there is this little particle, and it's actually traveling on this curve at 7 centimeters every second. So they haven't asked us a question yet, but the question that they are going to ask is this. Oops. Assuming the particle starts at 0 f of 0. So assuming the particle starts at f of 0, no, sorry, the point 0 f of 0, where is it after 4 seconds? So this is the question that we're going to try to answer, and we do know that in 4 seconds, we definitely know that it's traveled 28 centimeters. So in 4 seconds, the particle has traveled 28 centimeters because we're told that it travels 7 centimeters per second. So we really want to know the coordinates of where it has landed after those 4 seconds. And one way we can think of it is we want to know when the distance from 0 to something is equal to 28. We need to know what that something is, but we know that from 0 to some point, some x value a, that the distance on the curve, which we know to be 1 plus f prime of x squared dx, we need this to equal 28. And so we're really solving, we know what this is, they've given us the function. We're really solving for this a at what x value, and then we could calculate the y value of the curve. Does that particle attain, has it traveled 28 centimeters? So we're going to go ahead and jump over to Desmos and look at it on Desmos. Before we jump over to Desmos, I just want to stress that this is the formula, this whole thing for arc length. That's why we're using this expression right here. So here on Desmos, I'm going to put in that function 0.1 x squared plus 1. And we're going to try to calculate, we want to know when, at what point, this arc length becomes 28. And so what we'll do is we are looking for the integral of from 0. We know the particle starts at 0 and it stops at some point a. We're not sure yet what that is. And the arc length will be measured by square root of 1 plus f prime of x squared dx. And we're going to add a slider a. When a equals 1, so when you go from 0 to just 1, the arc length is 1.006. If you go to a equals 3, then the arc length becomes this quantity here. From 0 to 3, this is the arc length. And so we need an arc length of 28. So taking it up to even 10 doesn't quite get us enough. So if you were to go from 0 to an x value of 10, then this would be your arc length. But we need an arc length of 28, so we need to make this range larger. We'll take a from 0 to, let's take it to 30, and our step just will be 1. And so that sounds reasonable that this is how we could get it. So we want to get it up, the arc length up to 28. Okay, so here we are pretty close. When we go from 0 to 15, so remembering that these are x values on this graph, the arc length will be 28.2. That's a little bit too much, so we could say, okay, what if it's like 14? And 14 gives us an arc length of 25, so definitely not enough. So what about 14.8? Getting closer. What about 14.9? Oops. Definitely getting closer. So this is one way that we could kind of finally hone in on what the x value is for the point at which the arc length will be 28. But there is sort of a more elegant, sophisticated way to find this. So we're going to name a new function g of x, and we're going to let g of x be the integral function from 0 to some value x of our that arc length 1 plus f prime. Now x is doing a job already, so we have to pick a new variable, and we'll use t, f prime of t squared, and that'll be dt now. So this is a function that is counting. Let's take off our original function that the path is traveling. This function here is counting arc length. So for any, x value, this is a function that will count the arc length. And what we're interested in now is when is this function equal to 28? And so we can just put in a, y equals 28. So y equals 28 and find out where these two values intersect. And we can see that they intersect hopefully around 14.9, and that's the exact place that they intersect, is 14.91656. This is the x value that gives us the point at which the particle has traveled 28 centimeters. So again, this is a somewhat more sophisticated way to find, instead of just, this method of kind of refining, just jumping around trying to get this number to be 28. This is a function that counts your arc length, You have arc length, and you're going to just go from 0 to some x value, and this is counting your arc length. And we want to know when this intersects with the function y equals 28. We know that it intersects when x equals 14.91. Does that answer the question that they gave us? So let's go back to see if it answers it or if we're pretty close. Okay, so we're very close to our answer here, but we want to make sure that we're answering the right question. Assuming particle starts at 0, f of 0, where is it after 4 seconds? So they're asking for an x and y coordinate of where the particle is after 4 seconds. And we know that we've done a little bit of work with this function here. This was counting arc length. We know that when x equals 14.91656, that the arc length will be 28. That's what we needed to find out. So when x equals 14.9, that 14.9. So somewhere in here, the arc length will be 28 that particle has traveled. So it's 14.9, but we don't yet have the y value. We don't know what the y value is. And so this function did a good job figuring out for us at what x value we would reach an arc length of 28, but now we really need to go back to the original function and find out exactly where that particle will be. And it will be at, so the particle will be at, let's see, what was it, 14.91656, and then whatever the original function evaluated at that point is. And so right now we're going to go ahead and find that out. We just need to stick this into the original function right here. I went ahead and evaluated the function at this x value, 656, and the y value is, the corresponding y value is 23.2502 on the curve f of x after 4 seconds of traveling. Okay, so that was a good example to give us some practice with counting up arc length. We know how to evaluate arc length, but they didn't ask us exactly for the arc length. They asked us for it in a sort of roundabout way that we had to go searching for it. And we decided there were these two methods. I like this method better because it gives us a more precise, if I asked you to find it to 5 decimal places, you would definitely want to use this method using an integral function to count up that arc length and find out when that integral function is equal to 28. Okay, so we've learned how to evaluate area between two curves, and we've learned how to find the arc length. So a really good section.